Okay, over to you, Fernando.
Thanks a lot, David. Thank you everyone for coming to, attending this virtual seminar. So I'm gonna give you an overview of the research that we do for navigation and motion planning for UAVs flying in GPS denied environments. So today's content is about, first I'm gonna describe the problem of navigating in a GPS denied environment and executing a mission. So it's not only navigating, but also the UAV has a mission of, for example, surveying an area or finding a target. I'm going to describe the system architecture that we developed in order to achieve this. Some prototypes that we have developed for this. A proposed framework which combines SLAM and POMDP. And then I'm going to continue with results and applications, further work, and some acknowledgements. So the UAV navigation and mission execution in GPS denied environments. So we have a UAV flying in, if we have a UAV normally flying in a GPS enabled environment or a GNSS enabled environment, the UAV, you can basically program a mission in a software and the UAV will autonomously execute that mission. So it will take off and you program some waypoints or a pattern, a lone mode pattern, and the UAV is able to achieve this. But when you have challenging environments like natural canyons, or when you're flying below the canopy, or in urban canyons with lots of infrastructure, you have a lack of GPS signal, or the GPS signal is noisy. So that can affect the ability to fly in these airspaces. Some environments that we're focusing as well are environments which have obstacles in the airspace. The lack of GPS produces uncertainty in the localization. If we use other navigation systems to overcome the problem of the lack of GPS, these systems also come with some uncertainty. So we can use cameras with SLAM, but nevertheless, these systems also accrue some uncertainty. There could be dust or wind in the environment, changing conditions, lighting, appearance, and a limited payload capacity. We are focusing in small UAVs under 2 kilograms. I'm going to show you why this is important. And we're also focusing in a safe autonomous operation. So the proposed framework consists of hardware and software. So hardware, we have built prototypes or multiple prototypes, which are based on a quadrotor frame. We also put an onboard computer and visual inertial sensors so that the UAV is able to localize in a GPS denied environment. Also, it's worth mentioning that we're aiming to build a sub 2 kilogram payload, UAV, because the sub 2 kilogram UAVs are within the very small RPA category, or the excluded category for CASA. CASA is the Civil Aviation Authority in Australia. And they regulate the use of remotely piloted aircraft. So if you're using an aircraft which is under 2 kilograms, this falls under the excluded category, and it has some advantages, like, for example, not needing to get a remote pilot license. but you still have to comply with some regulations, like for example, registering your drone and registering yourself. So we're basically putting an onboard computer connected to the autopilot for commanding the UAV. We have visual and inertial navigation sensors, and we also provide a software stack, or have developed a software stack, which is based on the robotic operating system. We use SLAM, an open source SLAM package for this, and we're combining it with a reinforcement learning approach, which is based on the partially observable Markov decision processes for motion planning and execution. So we're using an online POMDP, which allows us to execute the mission and replan the mission and update the mission and keep track of the uncertainty as well. The software stack has been developed into different modules, and it also consists of modules for monitoring and safety. The system architecture, we have, in terms of hardware, we have a small UAV with an autopilot connected to the onboard PC. We have a depth sensor. We have tested different combinations using a depth sensor or using a visual inertial odometry sensor. So 2 different sensors connected to the computer, or just one sensor which acts as both. We also have a remote control and telemetry, and we also use a point LIDAR to avoid, or for safety, for estimating the height over the ground. There's also a ground control station in which we have a PC basically, which also connects through or via Wi-Fi and with a telemetry radio directly to the autopilot and directly to the onboard PC. Finally, we have a remote controller, and the operator is using this remote control as well for safety. So we always fly with a remote control. Also, in terms of regulations, this is always needed. You always need to fly in line of sight of the UAV. And in case something goes wrong, we need to have a way of recovering the drone and take control of the drone. So this is very important. In terms of software architecture, we use a modular system in which we have a motion planner algorithm running the motion planning, depending on the mission that we're using. So we can have missions, for example, for target finding or for exploration of unknown environments. And there is a formulation for this. So more on this later. This motion planner sends commands to a motion command server, which is running is running as a ROS node. And in this also sends through MAFROS the commands to the PX4 firmware. So we're running a PX4 firmware on the autopilot on the UAV. This is also an open source software. We also have an observation modules ROS node, which receives observations from the sensors and also from MAFROS, and it updates or sends these observation updates to the motion planner so that it can keep track of what's going on and also adjust or send a new action that the UAV needs to execute. In order to fly in a cluttered space full of obstacles, we need an occupancy map. We need a way of telling how to avoid the obstacles. We're using Octomap for this. So the SLAM algorithm which we use is RTAP-map, which produces an Octomap in real time as well. This SLAM algorithm takes inputs from the depth sensor and from visual inertial odometry sensors as well. Those sensors will use a ROS driver. And on the ground control station computer, we have also ROS running for monitoring. So we have a visualization. We can visualize in 3D the point cloud and the map that is being generated by the SLAM algorithm. Also the pose of the UAV and the camera feed, for example, for target finding or for target detection. We also have a telemetry program which is connected directly to the PX4 autopilot for monitoring the health of the UAV. And we also send remote commands to the onboard PC. So basically we connect through SSH and start the system on the onboard computer. So a good thing to mention here is that we're relying on an onboard computer for executing the mission, because if in any point in time we lost a connection, there's still the safety of running this modular system on board the computer and on board the UAV. In order to develop this system, we need to start by testing first the localization of the system. So we use a Visual Inertial Odometry algorithm for this. And we start testing in an indoor environment. So we have QT has a flight arena, a flight testing capability facility that allows us to test UAVs in a netted area, and also we have a motion capture system. This motion capture system allows us to compare odometry. So in this case, the UAV is flying. We have the top view from the UAV, but we're also capturing its motion with the motion capture system. We use a Vicon system. And this allows us to compare the localization of the system. So if you see here, when the UAV starts flying, both frames are more or less aligned. We have the Vicon frame, which is act as the real world frame. We have the map, which is produced by the SLAM algorithm, and we have the Odom frame, which also varies. Once we place the UAV on the flying arena, we need to capture the relationship between the Vicon and the map frame so that we can compare. So we're able to do this. And then this allows us to compare both the odometry with the ground truth. You'll see that it will drift, especially with rotations. The UAV is performing a sequence of waypoints as well. So we have developed software that allows us to send commands to the UAV, motion commands, basically post commands. At the end, the UAV, once it closes a loop, so it basically travels a square pattern, and then once it closes the loop, the error is reduced, as you would expect with the SLAM systems. Then the next test is to show how the map is built. So we also do, so this is the place where we are building a map. So in this test, we're just doing a handheld mapping. And we're visualizing how the system is building that map. In this visualization, the UAV is, well, this is fast tracked, fast forward. The UAV, we're holding holding the UAV with the hands, with our hands, and mapping around. So this is creating, what you see there is just a 2D projection of the 3D occupancy. This is an occupancy grid. And you will see that at the end also, it once it closes the loop, it does, the algorithm does some corrections and it adjusts the map. So you see that it's adjusting the map. So we finished the mapping, but it's finding new loop closures. And you will see here the point cloud that is generated for the octomap, for the occupancy map as well. And the frames for the UAV, for the whole system, the important frames. So with this occupancy map, we can now generate a mission and also fly safely. We have been testing, so QT has a property which is called the Sanford Ecological Research Facility. This allows us to test the system in an outdoor environment. So the idea of testing this is also for obstacle avoidance, for avoiding trees. So this also comes from the goal of the project, of an ARC discovery project, which is to navigate below the canopy, to navigate safely below the canopy. SURF allows us, it's a place that is close to the Brisbane city, but it requires planning. So you have to book the place for flight testing. You have to request permission to do flight operations. You have to submit a flight plan. There should be a maps, a risk assessment also that needs to be approved before flying. It also requires logistics, booking or renting a QT car, packing it up, loading, gazebo or marquee, table, chairs, and generator. But it's also fun. It's really good. It's a really good experience. It can be too hot in summer, but it's a good, really good. It has also good spots to test flying below the canopy. Okay, so I'm going to show you a a test of flying manually the UAV with RC, but the position is coming from Visual Inertial Odometry and SLAM algorithm. So we're doing manual piloting in position hold mode, which is an easy way of piloting UAVs once you have either GPS or this system for positioning. We're monitoring with a ground control station as well to record the data. And you will see that we have some challenging conditions. So in this case, there was a draft, and you will see a lot of debris and dry leaves, and there is downwash from the UAV. So sometimes this affects a lot. It basically it comes in front of the camera that is used for SLAM, and it affects a lot the performance of the SLAM algorithm. We've been doing also some outdoor flight tests for, well, the other part that we want to check is the 3D reconstruction. So this is a 3D reconstruction, a point cloud generated by the SLAM algorithm of this place on the left. So the algorithm generates three main products. One is the 3D reconstruction, the other one is the localization, so that the UAV is able to fly, and the other one is the occupancy map. So you will see that it is creating, so you could translate this into an occupancy map to avoid the trees. Still, there are some challenges that we need to solve. You see that the trees sometimes appear as flat, and this is the occupancy map generated. But this is enough. We believe that this is enough for us to, or for the algorithm to do a planning to the motion planning to avoid the obstacles.
Hey, Fernando.
Yep.
We have a couple of questions come through to me.
Okay.
One of them, both of them are from Bilal. One question, which sensors have been used on the UAV to measure scene depth?
We have used 3 different kinds of sensors. You could see here in the, thanks for the question. In these prototypes, we have used 3 different kinds of sensors. So we use the Intel D435 combined with the Intel T265. So this is depth. It projects, it uses a projected pattern. And we also used a time of flight camera, which is this one. It's now discontinued and maybe the company is not running anymore. This sensor is a good sensor for indoor environments, but it has a very short range, so only up to 4 meters. And we're currently using the Z2 camera, which allows us to have both visual inertial odometry and depth in the same sensor, but it requires an NVIDIA Jetson computer. So, yeah.
Excellent. The second question that was had was, how is the depth uncertainty being used in the POMDP states?
Yeah, thank you for the question. What we use, let me just go back to. So what we use, the depth sensor basically is used for the SLAM algorithm. The SLAM algorithm produces the occupancy map, and we use the occupancy map in the POMDP, so that's the relationship. So we're constantly looking at the occupancy map in the POMDP, and we query the occupancy map to check for possible collisions. So the way that the POMDP works is that it has an internal simulator. It has the dynamics of the UAV. We model possible actions that the UAV can take, and then based on this, it predicts based on the actions where it's going to be and the outcome if it's possible that there is a collision. Looking at the octomap.
Excellent.
Okay. So continuing.
Thank you.
Okay. Continue with the framework. So we use PX4 firmware. We use MAFROS, which is the bridge between PX4 and ROS, and we also use Gazebo for simulation. Let me show you more the workflow that we use. So we model the problem as a POMDP. So we model the states, possible actions that the UAV can execute. For example, going forward, rolling left or right, going up and down, or changing orientation. We model the rewards according to the mission plan. So depending on the mission, if we want to find a target, we give positive high reward to the target. And if we want to avoid obstacles, we give a negative reward. We model the observations. So for example, if a target is detected, or the pose of the UAV, and also the map that is being created. We also model the dynamics. In this case, we need to model according to the actions that we select. We can model the dynamics. So we test in the lab how the transient basically between or after applying an action, and we model this as third or fourth order system for each of the modes that we're using, or for each of the degrees of freedom that we're using. And we also model the uncertainty. We model the uncertainty as using a Gaussian function, for example, a noise using a Gaussian function. Then we simulate this, we do a first run of a simulation of this system. For that, we use the PX4 software in the loop. We use Gazebo for simulating this. We can simulate Octomap, and we can even simulate SLAM running with a depth sensor in Gazebo. And it's a ROS-based system. Then we proceed with the flight test as well, or in parallel, flying indoor and outdoor, testing the SLAM, testing the occupancy map. And the next step would be the POMDP with the SLAM integration. This is also in simulation and in flight tests. So the integration of the POMDP and the SLAM in a simulated environment is shown here. The UAV can perform actions. So if you see, the left is a simulated scenario, and on the right, you see the 3D occupancy map. We have a first belief state. So in the POMDP, we use belief states, which are represented by particles. So the particles represent the probability of being in a state. So they also represent the uncertainty. The red particles represent where a possible target could be. So it could be anywhere within this region. So we're just restricting, in this case, the search area within this square. And the white particles represent the UAV position. Oh, sorry. We also model that the UAV has a downward looking camera, and we model the field of view of this camera. So if there is not a target within the field of view, then the UAV will continue searching, but the particle filter will clear out the particles that don't belong to the received observation. In this way, we're forcing, if we don't have a target here in a real scenario or in this simulated scenario, we're forcing the UAV to explore around the whole region and map at the same time, so creating an occupancy map. So you will see that the red particles disappear. The red particles representing possible targets disappear as the UAV moves and explores the area, and also the occupancy map is being created. So let's fast forward. You will see that the UAV already has cleared out this space, but at the same time, it has mapped all this space. And it continues mapping. So this is the way that we simulate. I'm conscious of time. So I'm gonna show you some applications that we have done of this platform. For teaching purposes, we develop a project for EGH 455 unit, in which the students need to create a payload. So it's a payload that is independent from the UAV, but you can connect it to the UAV. And this payload is for monitoring environmental variables and also finding targets. So we put some targets around the flight area. And we program just a square pattern for the UAV to fly around while using the payload. So we have a ground control station. So this is the UAV is performing those waypoint navigations autonomously. But at the same time, the other payload, the developed payload by the students, is showing some environmental variables like gas, for some gases, detection of some gases, pressure, barometric pressure, and at the same time also the target detection. At some point, the targets are being detected, and it's also showing the humidity, pressure, and some variables. So that's one of the applications of this framework. So if we continue. Another application, Juan Sandin, a PhD student, has been working on people and object finding. We did a collaboration in which he used the Visual Inertial Odometry for indoor localization for detecting a target. In this case, it's a person in a search and rescue scenario. The formulation of the search is also based on the BOMDP and based on actions that the UAV can execute. So the UAV moves around the scenario, searching for targets. But in this case, the map is not updated, it's just a fixed map. So we're using Octomap as well for the occupancy map. And we also, well, in this research, Juan also did some simulation. So to conclude, future work and recommendations. So the flight test of integrated SLAM motion and planning system for autonomous exploration and target finding, that's currently ongoing work. We're testing the integrated system in a flight test using an NVIDIA Jetson as a companion computer. We're also looking at using photogrammetry integrated with the SLAM for 3D reconstruction to improve the 3D reconstruction. We're looking at comparing the SLAM that we use with the, for example, Veins Fusion or other open source algorithms. And also doing ecological assessments, applying this framework for ecological assessments. For example, animal detection. Imagine the UAV navigating below the canopy and detecting wildlife, vegetation, or doing an assessment of the forestry. With Toby, we had a look at possible ways of exploring the use of event cameras to improve the 6D of SLAM, also in low light conditions. And there is another PhD student working on a multi-UAV target finding. And also POMDP formulation for planetary explorations. So I would like to acknowledge Associate Professor Felipe Gonzalez, who is responsible for the ARCDP, which funds this project. Also the QT Ref team at Da Vinci Present, which is supporting technical aspects of the flight. QCR, the providers the Vicon software. HDR students, Juan Sandino, Nicolas Mandel, Juan Galvez, Julian Galvez, and Ed. The Sanford Ecological Research Facility, Professor Kevin Gaston from University of Exeter. Professor Joe Roberts, also part of the DP. We use Hannah Karniwari ABT software and science and engineering lab technicians. So thank you. We have some references. And do you have any questions?
Thanks very much. Fernando, do we have any questions from the general audience first? Frederick, are you unmuted?
Yes, I have a question, Fernando. What do you need to provide to the POMDP software in terms of modeling of the dynamics of the UAV so that it can solve the POMDP?
Yeah, we need to provide We model the dynamics depending on the actions that we select. So if we select, for example, actions to go forward by pitching forward, the PX4 firmware, the PX4, the autopilot can control the speed, and it can also control the position. So what we measure basically is we model how the UAV transitions from being hovering to any waypoint or to a particular waypoint. So we model through velocity commands or through also position commands. So basically, what we do is modeling the transition, the transient.
So is there a calibration software, or is it something that you have to compute manually or by other means?
We run tests. We acquire the data using the Vicon, the post basically, how it transitions, and then we use MATLAB to create a step response. Basically, what we're doing here is providing step inputs. We're seeing how the UAV responds to those step inputs.
Okay, thank you.
Thank you.
Thierry, you have your hand up, so I'll let you go next.
Thierry.
Thanks for the talk, Fernando.
Thank you.
I've got a few questions, so I'll just stick to two for the moment. The first one is, of course, as Michael alluded, the task that you're trying to achieve is very hard. Of course, there's no doubt there. Anyone who has tried would know that. Can you give us a good better feel of what you can do at this stage and what you target to be doing by the end of the DP? I mean, realistically, not what was written in the grant, right? Just that's like realistic objectives for what are things you can do at the moment, what are things you can't do yet, what are the limitations, what are the challenges? And the second part is, do you think that you may need later semantics in your representation, and have whether that would help significantly, or are you basically happy with your occupancy map as long as you have a good one?
Okay. Good question, thank you. The first one, what we can do is the UAV can perform actions. So we have that. So the UAV can localize itself in a GPS denied environment to a certain accuracy, depending on the sensors used, and also depending on the visual inertial odometry algorithm used. But in any case, it's also producing an occupancy that allows us to, in its own frame, check for possible collisions. So we have motion commands also. We can command velocity and position commands to the UAV, so we can command actions. So that's part of the module of sending commands. What we're missing is the integration between the POMDP, or basically what we're working on now is flight testing, the integration between the POMDP formulation and yeah, the whole system basically integrated. So that's what we're working on. In terms of the second question, the semantics, yes, I mean that would be something really useful if we can combine that. I think there is a way of modeling that into the POMDP in a higher level than just querying an octomap to see if there is an available or a free space or an occupied space. And it will also, it's like maybe going in, increasing the level of the actions that we're doing. We have a kind of intermediate level in which we're relying on the motion control of the PX4, but we're just sending commands to go forward, left, or right. if we have semantics, I think we can do going to a particular place like with meaning. Like for example, if we're in an indoor environment in a building, one of the actions could be navigating to a door or navigate a hallway. Yeah, those kinds of things. So yeah, I think semantics could increase the functionality of the system. Thank you.
Cool. We have one more question that was typed to me that I'll read out from below. So how is the POMDP accounting for the sensing uncertainty, in particular the forward camera, while you have considered only particles on the ground? What is the probability of the cell of the occupancy map?
There are two things. One thing is we're modeling uncertainty in the localization. So we're adding basically a noise and a stochastic part to the dynamics as a Gaussian noise. This also can be replaced by the SLAM, what the uncertainty provided by the SLAM, for example, with through covariance matrix. And the other thing is the uncertainty in the target. So we have two types of uncertainty, and we're modeling those two types differently. So when we model a downward-looking camera, so we're modeling basically where the uncertainty where the target could be. So we're not modeling the uncertainty, the localization with the downward-looking camera. We're just making use of that to force the UAV to explore the area, basically. If we had a forward-looking camera, then we will need to model it with the field of view. It's a bit more challenging, I would say. I don't know if that's responds the question for Bilal.
Bilal?
So you're using the forward-looking camera for the Z, like Z2 or something?
Yes.
So you are not considering that as part of the training of the POMDP, or like?
No. No, it's not part of the training of the POMDP.
You're not considering that one. Yeah, that I understand. But when you are building the occupancy map, for example, the octo map, there is a particular probability you have to set it that it's free or not occupied or something. Octo map framework. So what is that? Are you measuring it or dynamically changing it, or it's just a static hardcore value?
Yeah, thanks a lot for the question. The map is changing. And we basically the POMDP planning is changing in every step. That's why we use an online algorithm. So we start with basically what is in front of the UAV when it is on the ground. It does the first plan based on that. So it's basically, it does the first offline planning. The POMDP plans based on that, on the first view of the map. And then once there is a time step, it updates the map. So the POMDP plan basically is discarded and replanted every time. But we keep track of the belief space, of the belief state. Sorry. Does that respond to your question?
Yeah. That's fine. Thanks for the answer. Yeah.
All right. Well, we are now over time in basically the usual amount that we usually are. But thank you, everyone, for the discussions and the questions. I'm sure if there's anyone else who has a burning question, they can go contact Fernando directly and find out more about the stuff he's doing. But in the meantime, everyone, let's just thank Fernando for a wonderful talk.
A quick one, David. Just to conclude on a nice note. Fernando, just a quick one. Do you have any video of a nice crash of a UAV because of small branches or something in the environment? And if you don't, may I suggest you actually do some and then use that as a motivation at the start of your talk? That would be, I think, very effective.
Yeah. Thanks. We have some drifting. We don't have a crash video per se, but
just ask Felipe. He has a bunch of spare UAV. Just use one and crash it. And, one of the old ones or something.
Yeah, but we do have some drifts. So we with the UAV drifting away, not that much, but yeah, we had to cancel. We had to basically take it down, like through the control remote control, landing it, force landing it. Yeah.
All right.
Thank you.
Thanks, Fernando. Thanks, everyone.
Thank you very much for the talk, Fernando.
Thanks.
Thank you.